So here's the strategy that I would suggest. There's probably a couple different ways to do this. We could take the original graph that we know there is some length L path, simple path from U to V. And what we can do is for each edge in the graph say, well, what if we delete that edge? Is there still a path? And if the answer is yes, then we just leave it deleted. But if the answer is no, that we've now actually broken the path from, or a path, or the last path from U to V of length at least L in G, then we need to leave it in there. We keep repeating this until all the edges have been considered, and all that's left at the end will be the simple path. Why? Because if there's any edges in there that's not on the simple path, then we can delete it, and there still is a simple path. And certainly we can't delete any of the ones on that simple path and still have it work. So what's left is exactly what we need. So here's my attempt at that as Python code. So again, we check first to make sure that there really is such a path, and if there isn't, then we just quit before we try to find it. But if there is, so somewhere in there the path exists, what we're going to do is run through all the edges. So node 1 in G, look at all the neighbors, look at node 2, which is a neighbor of node 1. So now node 1, node 2 is an edge in the graph, and we're going to break the link. I probably should have mentioned that earlier, but there is actually a break the link piece of code in the skeleton that I gave you. So in graph G, get rid of the edge from node 1 to node 2. We can do that in constant time. And now we ask, is it the case that there's still a long and simple decision, a long and simple path? We ask for the decision, is there a long and simple path in G from U to V of length L? And if the answer is no, if there's not such a path, then we need to put that edge back in the graph. Otherwise, we just leave it out. We repeat this for all the nodes, all the edges, and then we're basically done. All that's left in G is exactly the simple path, and now we have to read it out. And it's a little bit messier than I thought it would be, but it's definitely doable. You could run as a graph search on this graph, and that would work, because all that's left is the path that you want. But another way to do it that's more specific to this case is we start off building our path from U. And we're going to have a variable node, which is a particular point in the chain, and a variable next, which is a next point in that chain. And we start that off with whatever is the neighbor of U. Notice there can only be one neighbor of U because all that's left is the simple path from U to V. But, okay, all right, so now we say as long as that next node that we're looking for isn't V, we append next to the path so far, so we have the first two steps. And now we're at a new node. This node next is going to have two neighbors. One is going to be the node we just came from, node, and the other one is going to be a new node that we haven't considered yet. So just to figure out which one it is, and what I did is I just pulled the two of them off. I said let next 0 be one of those neighbors, and next 1 be the other. If next 0 is the node we just came from, then we're going to move one step along the chain. Node gets next, and next gets next 1, the one that we haven't visited. And otherwise, next gets next 0, the one we haven't visited. When that loop is all through, then next is V, the very last step on the path, and we just add that into our path and return it.